Hello, Year 10, and welcome back. Today we'll be looking at forces and braking, and specifically the overall stopping distance and how that stopping distance is made up of two factors, braking and thinking distances. Okay, what I now want you just to reinforce is that actually you have got access to the online textbook. So if you are bored by any chance by the sound of my gorgeous voice, you can just log on to Caboodle and make your own notes. Alternatively, you can make your own notes whilst listening to me, up to you. However, from now on, we will be putting the Caboodle link on the front page of all the slides, and I'll also be putting it on Show My Homework. So, for today's lesson, you need page 126, and they're the pages for the previous lessons if you haven't managed to do the work for those. So just 1 to 10 quickly in your margins for me. Have a quick go at these 10 starter questions. So the first one is, what is the equation that applies to Newton's second law? It's force equals mass times acceleration. Remember, you can put that into your triangle. Number 2, applying Newton's second law, will acceleration increase and decrease if an object's mass increases? Decrease, because acceleration is inversely proportional to mass. What does resultant force mean? It is the single force that has the same effect of all the forces acting on it, acting in different directions. Number 4, calculate the resultant force of a sprinter with a mass of 80 kilograms who accelerates for 8 meters per second. So force equals mass times acceleration, so that's 80 times 8, giving you 640. Remember your units, newtons. Number 5, applying Newton's second law of motion. If the resultant force is 0, what will happen to the object? It will remain still or continue with a constant velocity. What is the equation and units for weight? Bonus points here. And weight is kilograms. Okay, lots of confusion over that one, but weight is a kilogram. Terrible, I've just said that wrong. Weight is newtons, mass is kilograms. I'm terrible. Don't tell Mr. Collins. Right, number 7. What does the term terminal velocity mean? It's an object has reached a constant velocity where the frictional forces acting on it are equal and opposite to its weight. Okay, so it doesn't matter how much we increase the thrust or the weight of the object or streamline our object, the frictional forces are equal and opposite to any modification that we have made. This is really number 8. So number 8, what is the resultant force when an object reaches its terminal velocity? Resultant force is 0. Interesting fact. And a bit of revision for chapter 9. What does the gradient of a line on a velocity time graph represent? And it represents acceleration. And revision for chapter 1, and a bit of a challenge for those of you who are up for an exciting bit of physics. How are the equations for gravitational potential energy and weight linked? Let's look at this. So gravitational potential energy, small p, notice that, is equal to mass times gravity times height. Okay? Or you can just do mass times weight times height. Clever stuff. Okay, let's move on with today. So, forces on the road. Now, this often appears on the foundation paper and often appears on the higher paper because the majority of you at some point will learn to drive, and therefore it's one of the things that they can also test on this paper, and ironically factors that affect reaction times on the biology paper, because it's something that you will be responsible for. It's that social education that comes embedded into the exciting world of science. So the car image is travelling at a constant speed of 70 miles per hour on a motorway, and the engine provides the thrust to move the car forward. What other forces are acting on my car? Let me think. What have we got? You could draw a little picture of a car and label it if you're feeling so inclined. So we've got 4 here. We've got air resistance, okay, acting to slow the car down. We've got gravity holding the car to the road. The resistive force, the upward force of the road. Friction between the tyres and the road. Okay, make sure that when you're drawing these on the car that you draw the directions in which they're acting and the point at which they're acting. It's no good just putting arrows on it willy-nilly, okay? So, as the car is maintaining a constant speed and direction, the driving force and thrust of the engine are resistive and mainly air resistance are equal. What would the resultant force be? Look, it's a little red car. Isn't that sweet? So, the resultant force will be 0 because the forces are balanced. Because in the stem of the question, we talked about the fact that it was moving at a constant speed of 70 miles per hour. So, stopping distance. Now, this is the distance that you travel whilst applying a force to the brake. Okay. Now, there's lots of confusion over this about thinking distances and stopping distances and braking distances. We need to make sure that we're only talking about the distance you travel, okay? So remember our lovely equation, force equals mass times acceleration, which would be needed the greatest force to stop. So if I look at my lorry, yes, the lorry is going to require the greater force to stop because it has a greater mass, okay? So therefore, my object has more inertia because it has a greater mass. Now, let's think about other things that will affect its ability to stop. If it's travelling at a faster speed, okay, then it will take a longer distance for it to stop. Because actually, the time that we travel whilst we're thinking about stopping and the time we travel whilst we're applying the brakes, the distance we travel, will impact on our overall stopping distance. Okay, so look at the picture on the screen. Write down everything you can think that can cause crashes. Just take a minute, pause the slide. So, things that we need to think about. Reaction time, lack of concentration, drink driving, don't do it, it's dangerous, guys. Alcohol, drug use, don't do drugs and drive. Speeding, tiredness, how to take a break whilst driving. Mechanical problems, weather conditions, driving experience, road conditions, all of these things. There are many contributory factors. So basically, if the driver doesn't, it all boils down to if the driver doesn't stop in time, then they're going to hit whatever it is they're trying to avoid. So in 2018, 1,700 people died on British roads, 58% on country roads, and only 6% happened on motorways. Fun facts there. Why do you think there were more deaths on country roads than motorways? Yeah, let's think about that one. Well, people tend to drive faster on rural roads, especially if you think about around the lanes around Sevenoaks. So motorways have more speed cameras, which deters people from driving, making them safer. Out of the 1,784 deaths, 13% of those were related to alcohol, and 20% of all accidents were caused by tiredness. So, as we see, our motorcyclist is travelling towards our cat, and he sees the cat and he begins to slow down and then stop. If we think about it, how long does it take the moving vehicle to stop? That is our overall stopping distance. We have our thinking distance, and that's the distance we travel whilst we're thinking about stopping. Okay, and before we apply the force to the brake. Whereas the braking distance is the distance we travel whilst we're applying the force to the brake. Okay. And stopping distance is the sum of these two distances, whereas, and we need to be able to represent that simply as an equation. So stopping distance equals thinking distance plus braking distance. So those of you who are learning to drive a moped or are hoping to drive a car, this will be something that they test you on your highway code. So again, this is real world science. So these are thinking distances and stopping distances represented. Thinking distances in the blue, braking distances in the red, and the overall combination of the thinking and the braking makes our stopping distance. And you can see that at 20 miles per hour, my overall stopping distance is 12 metres, whereas at 70 miles an hour, it actually goes up to 96 metres. One of the things that they want you to be able to do is explain how these are linked, and this often forms part of a longer answer question. So what we've got here is I want you to think about 3 sentences you could write about this information. Pause the slide and use the sentence starters. So let's match some keywords, and I suggest you write these key terms down so that we're familiar with using them, because again, definitions are commonplace on the physics paper. So we've got stopping distance is the sum of the thinking and the braking distance. Friction is one of the forces that the road exerts on the car tyres as the car tyres are stopping. Okay, thinking distance, the distance the car travels before the brakes are applied. And braking distance is the distance the car travels whilst it's braking. So, if we think about this, this is affected by three main things. This is our thinking distance. How fast the vehicle is travelling, how alert the driver is if they're on drugs, tired, alcohol, carelessness, and old age, okay? Older people over the age of 70 are much more likely to have an accident due to being not as alert. Visibility, so if there's fog, rain, okay? And one of the other common ones that they want you to think about are mobile phones, okay? So they want you to often talk about the distractibility of mobile phones, radios, etc., etc., okay? So braking distances affected by four main factors. First of all, how fast the vehicle is travelling. So that's not different to the thinking distance. The mass of the vehicle, because that would be its inertia. If the car is poorly maintained, so that's the quality of the brakes and the tyres. The road conditions, okay, and that will affect the frictional forces between the tyres and the road. Okay, so let's just recap. Put these into columns, okay? Which ones are going to be affecting thinking distance? Which ones are affecting braking distance? So, vehicles and forces. So think about this. Why can an icy road increase the stopping distance of your car? Now, think about when you've tried to walk on ice and when it's been slippery outside, or if you've been on the AstroTurf and it's been wet, okay? How does that increase the stopping distance when you're trying to run fast and slow yourself down quickly? So the road will be smooth, so there's little or less or reduced friction between the road and the tyres. Therefore, the forces are unbalanced, and you will the car will stop moving. So the deceleration of the car is totally dependent on friction between the brake pads and the wheel, and the tyre and the road. Okay, now by making the road flat and reducing the frictional forces, your ability to decelerate is going to be made more difficult. Deceleration is calculated using motion time graphs. And deceleration, here's the equation for you guys. Ta-da! We do need to know that one. And let's go through a worked example. So, car with a mass of 1,500 kilograms. Car's mass doesn't change during its journey. Okay. It's travelling at 22 meters per second. It then stops at 50 meters. What is its deceleration? So, you then do 0 squared minus 22 squared divided by 2 times 53. Gives me 4.6 meters per second squared. So challenge, what would the car's braking force be? And therefore, we apply force equals mass times acceleration. 1,500 kilograms times 4.6 gives me 6,900 newtons. Okay, test your knowledge. Here we go. Car is moving along an open road. Suddenly, a sheep walks into the road. What do we call the distance between where the car travels when the driver puts their foot onto the brakes? The thinking distance. One factor that could increase the distance while the car travels in this time: medication, drugs, speed of car, tiredness, alertness, age. Okay. The braking distance is 35 metres for the car. If the stopping distance is 15 metres, how far did the car travel before the driver put their foot on the brakes? 50 take away 35, guys. Do the maths. We can do this. Ta-da, 15 metres. Right, last one, D. Calculate the deceleration of the car. It was travelling at 56 miles per hour, 25 metres per second, and when it is applied to the brakes and stopped in 50 metres. So, using the equation again, 0 take away 25 squared divided by 2 times 50 equals 6.25 metres per second. Now, practice skills. What I'm going to do is have a go. The attachment doesn't show my homework. I've loaded it. I want you to have a go at the bump up your grade. And you're going to email this to Mrs. Walker, and she will mark it and sign it off and show my homework. Okay, I'm not going to mark this one. Mrs. Walker's going to do it. So make sure that you do the sheet, and if you need me to post it home, email me, and I will be in school on Thursday, and I will post at home any that need physical copies because you run out of ink, whatever. All right then, take care, and I'll see you soon.